Well, first of all, thanks a lot to the organizers for putting a really awesome meeting together on such short notice. It's been a lot of fun and really thought-provoking, I think. The problem for me is that I guess a lot of the material I want to cover has already been discussed, especially yesterday in Manuel's talk and also in the talks by Peter Caldwell and Ben Sanderson. So I decided to change up my talk a little bit to include some preliminary results that a few of us have been thinking about, which, hopefully try to answer some of these issues we've been having with emergent constraints in CMIP6. And I thought this might be a good place to put them out there and stimulate some discussion, and it'd be great to get feedback on what we're thinking about. So I'd like to acknowledge Joel Norris and Casey Wall at Scripps, who I've been talking about this with, and also Max Pop, who's at the LMD in Paris. So to start off with, similar to how Ben Sanderson characterized things yesterday, I like to think of there being three different kinds of emergent constraints on ECS. The first is based on historical warming, which I think of as, given the evolution of greenhouse gas forcing, aerosol forcing, and land use, changes in land use, et cetera, and also in the time evolving, given a time evolving rate of feedback, can models reproduce, or how accurately can models reproduce the observed evolution of surface temperatures, particularly over the last 40 or 50 years. The second kind of emergent constraint, which I think has really been pioneered by our fearless leader, Peter here, is looking at temperature variability. And the question there is, do models with larger temperature variability have higher climate sensitivities? And then the claim is if we can measure temperature variability, observe temperature variability, that can tell us something about Earth's ECS. And then finally, there's these low cloud-based emergent constraints, which are basically just asking if models have the right cloud physics. And we want to try to interrogate this physics at shorter timescales and hope that there's something sort of climate invariant about clouds. A number of these have been proposed. So for example, this one by Briand and Schneider, which they published in 2016. And sort of as an aside, something I haven't really been able to wrap my head around is the fact that these low cloud-based emergent constraints tend to put ECS on the higher end of the intermodal range, whereas temperature-based emergent constraints, so either the first two, tend to put ECS on the lower, in the lower part of the distribution. And I don't really know how to reconcile that. But today I'm going to focus on these low cloud emergent constraints. And one way one form of these emergent constraints, which I like to think about, are regional low cloud emergent constraints. So looking at month-to-month or interannual variability in CRE, in cloud radiative effect, and how that correlates with equilibrium climate sensitivity across models. So this is a figure looking at this from CMIP5, where I've binned all the surface temperatures and series in historical simulations into 5-degree by 5-degree boxes. And then I look at the correlation across models in each box with ECS. And what pops out generally are these regions on the edge of the stratocumulus decks, particularly in the subtropical North Pacific, which seems to be very well correlated, where the variability in clouds here tends to be very well correlated with ECS. What I like about this approach is that it avoids mixing different regions and different regimes. So even if we're looking at two different stratocumulus regions, there might be differences in local weather conditions such that they shouldn't exactly be grouped together. And it also leads to natural tests for robustness, because you can develop emergent constraints in different regions and then see how they can compare. Say, if I develop one in the North Pacific and I compare it with one developed in the subtropical South Pacific. But the problem is that all these correlations go away in CMIP6. this sort of echoes what, for example, Manuel showed yesterday, that in general, low cloud-based emergent constraints don't seem to work in CMIP6. And for me, the reason for this seems to go back to some work that Mark Zelenka showed actually on Twitter, which was that you can separate out the CMIP6 models into a group of high sensitivity models and a group of relatively lower sensitivity models. And part of the reason for these high sensitivities is the low cloud feedback over the Southern Ocean, roughly. So he used 30 to 60 degrees south here, where some of these high sensitivity models have stronger low cloud feedbacks in this region. Whereas in CMIP5, the sort of consensus was that the spread in ECS was mostly due to subtropical low clouds. And so I like to think of there being a kind of Anna Karenina principle in CMIP, where all high sensitivity CMIP5 models are alike, but the high sensitivity CMIP6 models or each high sensitivity CMIP6 model has a high sensitivity in its own way, which is exaggerating a little bit, but it does mean that it's difficult to use a single metric to constrain the spread of ECS in CMIP6. And so the question is, where do we go from here? If in CMIP5, we could say the variability in ECS is just related to the variability in subtropical clouds, but it's a more complicated story in CMIP6. And so what we've been thinking about is to constrain the regional cloud feedbacks. So taking another Zelenka figure, you can see that there's this region of, I don't know if people can see my pointer, but there's a region of negative cloud feedback between about 90 degrees south and 60 degrees south, then a positive cloud feedback between 60 and 30 south. Then we have the tropics and the northern hemisphere. So maybe rather than trying to constrain all this at once, we should be trying to constrain the feedbacks in each of these different regions separately. And so we've again taken this regional approach of looking at the variability in a given region and trying to use that to constrain the cloud feedback in that region. And so here I'm showing the sort of emergent constraints for the net cloud feedback between 90 degrees south and 60 degrees south, 60 degrees south, 30 south in the tropics, and the same in the northern hemisphere, based on monthly variability in the top row and based on interannual variability in the bottom row. And we're pretty pleased with how this comes out, where there's a number of statistically significant relationships which emerge. To do with the monthly variability at the extreme latitudes in both hemispheres, and then with the annual variability for the tropics and the mid-latitudes in the northern hemisphere. One region which we're very interested in is these extratropics in the southern hemisphere, which seem to be one of the main differences between CMIP5 and CMIP6. So at first, it's disappointing that it doesn't seem to work. This regional constraint doesn't seem to work. But you'll notice there's actually an outlier model here, which I never know if it's good etiquette to call out individual models, but this is the NOR ESM2 LN model, which has an outlier cloud feedback in this region, where it's much more negative than any of the other models. And this really messes with the emergent constraint.
That's 2 minutes, Nick.
Okay. If we take out this model, then in fact, we get a really nice constraint with R-squared value of about 0.7, which gives us hope that we could constrain the cloud feedback in this region just based on interannual variability. So just to summarize the talk, these cloud-based emergent constraints on ECS seem to fail in CMIP6, which I think is due to this new importance of extratropical clouds and in determining the net cloud feedback, which is the main source of intermodal spread in ECS. And so we're sort of advocating for a focus on constraining regional cloud feedbacks which in these preliminary results seems to work pretty well. There's a lot more work to be done, for example, to investigate how they work in CMIP6 and to add in observations, but so far the early results are pretty promising. And we think that this could be a way to sort of move, to take low cloud emergent constraints, or to make useful low cloud emergent constraints in CMIP6. So I want to end with one sort of final thought, which is that I wonder a little bit if this Anna Karenina principle affects the temperature-based constraints. If you can build a model in multiple different ways to produce a given ECS or TCR, then even the temperature-based constraint, we could be getting the right answer for the wrong reason, even in these temperature-based constraints. So I think in a way it's fortunate that they tend to predict that the lower sensitivity models are more accurate, because I think these models are more consistent between CMIP5 and CMIP6 versus the high sensitivity models. Okay, thanks. Yeah, I'd really appreciate any feedback or thoughts that people have.